NSEM for everyone will happen offline. And it will be a 2-hour test. There was a clear, I think, instruction from the institute.
So, sir, we have been told that it is up to the professor. So, some professors are taking online test only.
I don't know. I mean, the mail that I received yesterday, it said it was a very clear directive that it is going to be an offline 2-hour test. 2 hour. That also was mentioned. In fact, let me see if I can open the mail. It was very clearly mentioned that it will be offline. So I'll let you know. And the test is still some time. So this is the mail. The following may be noted for the execution of academic activities in the current semester. All students except first year UG students will be called to the campus before 31st March 2022 for the offline tests. A communication regarding offline tests will be sent to the student by the academic section shortly. The test will be a part of the continuous evaluation as declared earlier, and the duration of the test will be maximum of 2 hours. It is to be ensured that the students get enough time to answer the question paper. The question paper may be set accordingly. And yeah, so that's pretty much it. So it is offline. You are going to get a notification soon. At least that's what the mail that I received yesterday, that's what it says. But any problem with offline test?
Sir, a lot of people are not coming back to the campus because coming back to the campus has not been made compulsory yet. So,
No, so no. So that's what, if you heard the mail that I read out, right? That all the students will be compulsorily called back by 31st March.
Hello, sir.
Yes.
Sir, actually, like we are at our homes now, and like the semester will end in like less than 15 to 20 days. So like
Yeah.
calling just for NSEM, and we have to plan, like many of us are.
Yeah, I understand your point, but I'm not the best person to answer that, right? I mean, once you receive an email, I'm not sure if when the email will go, then I think
yes,
you can take it.
sir, we have received a notification from VP that it is not compulsory to come back only for 15 days.
Or is it? No, but see, the mail that I read to you is what I received. I mean, I'm not making it up, right? I just
Actually, that has not been circulated to the students, so we just
no,
wanted to.
I know. See, Sakshi, probably you didn't hear what the mail says, right? I read it again, right? All the students except first year UG students admitted through JEE Advanced will be called to the campus before 31st March for the offline test. A communication regarding offline tests will be sent to the students by the academic section shortly, right? So it says that it will be sent, and this is the mail that I received yesterday. So my request is, if you receive the mail from the academic section or from your faculty advisor, then I request you to take it up with your faculty advisor and voice your concerns. I will also talk to the faculty of the department and see. I'll tell them that few students are concerned that they have to come back only for 15 days or so. But then the decision is not in my hand, right?
Okay, sir.
Understand? Yeah.
Yes.
Okay.
And another concern we had, if the tests are to be offline, can you please share some tutorials with us so we can, prepare for the exam?
So the assignments I've been giving the assignments, right?
Yes, but
And
actually in other courses we are receiving tutorials also with the questions similar to the ones which will be asked in the exam. So like it is like some
so,
practice
so
for those
Sakshi,
type of questions also.
Sakshi, this is a 300 course. So there is actually, if you look at the course structure, there is not. I mean, there is no allocated time as such.
Yes, we understand that it's a 3 credit course, but other courses we have more of 3 credit courses this time. So they are not solving it in the class; they are just giving a tutorial for us to practice.
Hmm. Okay, let me see. I can probably give some tutorials, but then that. So the second part of the statement that you made, right? people are receiving tutorials and the exam will be similar to the tutorials, right? That I cannot guarantee. Even if I give you the tutorials, right, that I will not be able to guarantee. My point is very simple. Whatever is being taught in the class, if you understand the subject, if you are attentive, you should be able to solve the questions. I'm not sure how much
Sir,
tutorials help. Yes.
sir, also like another request, could you like solve some questions in class? Because like
Yes,
I
that's
personally,
yes,
yeah.
that's a good point. That's a good point, Angana. I was also thinking that maybe the assignments that I had given you, right, and the mid-semester questions, uh, is that okay if I solve those in a class? Is that okay?
Yes, sir, that will be okay. Because even if we go through the theory, it's a little difficult for us to like apply them for the first time in
Yes,
the
because
test.
in
So
the test we could not like no, we did not know how to approach the questions because we hadn't solved any similar questions. That's why we want
Mm-hmm.
some
So
practice sums for that.
yeah, I understand, but if you see, right, I mean, yeah, I mean, I understand that few of you may not have been able to solve, but there are others who have been able to solve. And also, if you see, right, to me, I mean, the questions have been, but anyway, that is my thinking that the questions, whatever has been given, is actually people should have been able to solve based on the discussions that we have had. But let me have a session then. Probably next week, one day I will take a session on all the questions that have been given on the assignment and the mid-semester. And hopefully that helps. But then in the end semester, I don't think we will have questions from whatever we covered in the earlier semester. I mean, in the before mid-semester, probably we'll have question papers but that, I mean, we'll see. Let's proceed for now. Otherwise, we will not be able to, complete the. I get your concern that some of the questions, if you can, get the solution and then probably start thinking. So I will make an attempt to do that. Okay.
Yes, sir. And just to confirm one last thing, we do not have to come in the physical class tomorrow, right? In Nalanda.
Yeah, so that's what see, I myself am in the campus, but then I didn't go thinking that students are not communicated anything to you. So tomorrow may not be, but I will talk to the faculty members, probably the HOD and the faculty advisors, and see what they have got to say. And if they say that no, you have to ask the students to come to the class, then I will send you an email that you have to be in the class. But maybe not for tomorrow. Let me figure that out, and then I will send an email to the class. Okay.
Okay, sir.
And also, it is the communication regarding the offline class had been that it would be in a hybrid mode. Now, whatever that means, right? That some people who wants to come to the class and there are people who are not even in the campus, right? So my feeling is if it is in a hybrid mode, I mean, almost no student will come actually physically turn up in the class, right? And then there's no point in me going to the class and sitting there alone. So, but I will talk to the faculty and I will let you guys know.
Okay.
Let's proceed. So we will be talking about inertial sensors, and we'll also, I mean, the context of looking at these sensors are to actually understand the effect of feedback, right? So herein, if you see the structure of the, the seismograph, so it is placed on, of course, a platform, and because it's seismograph, right? These can be used for measuring.
Have you shared this screen?
Oh, I didn't. Oh, sorry. Oh, sorry. Okay. Can you see now?
Yes, sir.
Okay, cool. Yeah, yeah. Sorry for that. Yeah. So this is a picture of a seismograph, and as the name suggests, right? We use this to measure seismic activities, right? Earthquake and stuff like that, and this is how it can look like. So it is cased. The whole thing, the sensor is housed in a casing, and there is a scale which kind of indicates how much the marker is going to move, and we have a mass m and a spring and damper arrangement. So if, let's say, the platform moves, which, let's say, is nothing but it is going to be placed on the Earth's surface, right? So if there is a movement on the Earth's surface, so let's say this mass m, so these are all absolute movement values, and this is y, and let's say this mass m, this inside the sensor moves by an amount x, and then the overall displacement in the marker is measured by z. So then we can say that z is equals x minus y. On the Earth's surface, right? So the actual movement is z is equal to x minus y. So now we also know, so this is again from the spring and damper, a force equation, right? The overall force acting on this mass m. This we have discussed in the piezoelectric, while we had discussed the modeling of the piezoelectric sensor, right? A similar equation of the mass sitting on a spring and damper system. So the acceleration mx dot plus b times x dot minus y dot, basically the actual displacement of seen by the damper and the spring is actually x minus y, right? So this is the absolute displacement x, and this is the absolute displacement y of the Earth's surface. So the force, the opposing force because of the damper is equivalent to b times, this is the damper constant, multiplied by the effective displacement seen by the damper, and similarly the force offered by the spring opposite to the mass, opposite to the force provided by the mass is k times the overall displacement or overall compression of the spring, right? And that equals 0. So this is from basic force equation acting on this body, right? Any questions up to this? It's simple to understand, not a big deal, right? So then if I rearrange, I put, I kind of replace this variable x with z plus y. If I rearrange in terms of z and y, because finally, why am I rearranging? Because I'm interested, the input is actually y, and the final measurement that I'm taking is actually z, right? X doesn't come into picture as such. I just took the help of x to kind of form the equation, the force equation, and from that, once I replace x, I see, I can the force equation takes the form of this, right? And then taking Laplace on both sides. I hope you people are aware of this, right? This again we have discussed in the piezoelectric class, but taking a simple Laplace transform on differential equations, y2 dot will be replaced with s square. So here, so we have z2 dot. Z2 dot is replaced with s square zs. Similarly, we have bz dot is replaced with bs. We have taken, the only thing that we have done is taken a Laplace here, that we are aware, right? So an integral, if we take a Laplace on the integral, what do we say? So this will be xs by s, right? And a Laplace on the differential is s xs, right? This you are aware, right? So if we take the Laplace on both sides and then we rearrange, we get zs by ys. Please note zs is what we are sensing from the readout given by the seismograph, and ys is the input that the sensor sees because of the Earth's movement, right? And then we replace s with j omega, and this term becomes, it's easy to understand, so this becomes this, and then I'm reorganizing this equation in a standard form of omega square divided by minus omega square. So this is a standard second order form, right? So, and what is omega n square is given by k by m. Both, please note, is a characteristics of the sensor itself. K is the spring constant sitting inside the sensor. This you can say is a characteristics of the spring, or it's a design variable in the designer's hand. Mass is also a design variable, and 2 eta omega n. So this term is nothing but b by m, right? A simple kind of replacement of the. I'm just rewriting the variables that we obtained in a standard form, right? And omega n square is given by this, and 2 eta omega n is given by this, right? Okay. And then if I do a little bit more math, and I divide the numerator and the denominator by omega square, and then I define beta as omega by omega n. So this you can think of as a normalized frequency. So if omega n is the natural frequency response of the system, and omega is, let's say, the normalized, the actual frequency of the input that is applied here, beta is nothing but, let's say, the normalized frequency with respect to the natural frequency of the sensor. We see that if beta is much greater than 1, if beta is much greater than, if we can make beta much greater than 1, then Z is actually proportional to Y. Z is actually proportional to Y. Of course, this minus term is there, but minus we can neglect. The magnitude, if you look at the magnitude, Z is proportional to Y. But what does that mean? So to make Z proportional to Y, basically, and that's what we should do, right? The Z should be proportional to Y, right? Because we are actually measuring, the seismic activity. So we should be having an output which will closely follow Y. But then to do that, what do we have to do? We have to ensure that this beta is much greater than 1, which means the omega n needs to be reduced significantly, right? So which, if we reduce omega n significantly, that is also a problem, right? That means the natural frequency of the system will be very low, right? So if the natural frequency of the system is very low, it will not be responding to a large range of frequencies, right? It will be filtering out any frequency which is larger than omega n, right? It will filter that out. But then, so basically we are in a contradictory requirement. We want to have Zs proportional to Y, Z proportional to Y, but in order to do that, we are seeing we will have to reduce omega n, and that has a direct impact on the bandwidth of the measurement that we can have. At least in this kind of a scheme, we'll end up with that kind of an issue, right? And then, so now I'm rewriting the same equation which I wrote in the previous page. I've just, if you see here, so this equation, I've just rewritten this equation in the previous page, right? And what I do is, instead of, I just bring the, I just do one more step now. Instead of measuring or trying to measure the absolute displacement, we are trying to measure the acceleration in this variable. We are actually trying to measure y2 dot, and hence I bring this s square term here, and once I bring this s square term here, we see that if omega n is much larger than the intended frequency range of omega, then if now if omega n is much, much larger, so now we have landed ourselves with a proper condition that if omega n is much, much larger than the intended frequency of use, then Zs by s square omega s is approximately proportional to 1 by omega n square. This is a constant, right? So if this is a constant, so that means now using the same structure, which we had problem in measuring the absolute displacement, but we see that if omega n is made much larger, and instead of trying to measure the absolute displacement, if we try to measure the acceleration y2 dot, right, then we land up with a proper equation wherein the output is proportional to the acceleration y dot, y2 dot multiplied with the proportionality constant, right? So essentially what are we saying here? That this kind of seismograph or an accelerometer, I mean this kind of a structure probably is not very good to measure the absolute displacement because we land up with contradictory requirements. However, if we are interested in measuring the acceleration and make this inertial sensor work as an accelerometer, then at least this equation is acceptable to us. Because omega n is constant, so we get the final output z is proportional to the acceleration. Any questions on this?
Hello, sir.
Yes, Saurabh.
Sir, in the expression of Zs by Ys, shouldn't be there like an in numerator, it should be minus ms square, right?
Minus?
Ms square. So m has to be there in numerator.
No, I have done the same. See, oh, you are saying, yeah, that maybe you are right. I think what you are saying is let me see. I think so. You are saying maybe a factor of m is missing, is it? That's what you are saying, right?
Yes, sir.
Actually, if you see, yeah, m, I've actually absorbed them in this. Actually, that's a good observation. I have absorbed. So what sort of you are saying is, yeah, this S I have brought all right here, but yeah, maybe one by m will come here. Yeah, you are right. 1 by m will come here, but that doesn't change. That doesn't change the expression. I mean, in the sense that we still end up with getting a final output proportional to acceleration, right? M is known to us, right? Even if this m appears in the denominator, right? M is known to us, right? So that doesn't change anything as such. Based on, I mean, in the present context of the discussion, yes, Saurabh?
Yes, yes, sir.
Yes. So yes, I think that you can work out the math and see probably I've missed out an m here. I'll also look at it and probably I'll get back to you. With a feedback put in place and see. So in the previous one, of course, we didn't have any feedback in place, right? But in this configuration, what we see is we have feedback being provided by this kind of a scheme. So here we have a magnet, and then we have a coil here. So this works like an electromagnet. So current flows through this coil, and this will generate magnetic field lines, as we know, depending on the direction of the coil, and of course the direction of the current. And the idea is very simple. The idea is so when this mass moves, what it does is we have a supply here. So this is a resistor here, and this pointer, instead of a pointer, we have like a probe which is moving on the resistor. So as this mass moves on this side or on this side, depending on the acceleration it sees, right? This probe will change the location from where we are actually tapping the voltage Vs, right? And this will go to a transimpedance amplifier. Why is it a transimpedance amplifier? because the output variable here we have is current and the input variable is voltage V, right? So when the output quantity is I and sorry, a transconductance amplifier, I take by point, output is I and the input is V. So we have a transconductance amplifier. So this is GM, and this GM is what this transconductance amplifier is going to do, is going to give a current which is proportional to the movement of this mass M, right? And this current, once this current changes, this will change the electric field lines generated in the coil, and that will either attract, I mean, depending on the field intensity, either it will get attracted to this side or it will get repelled, right? There is a equilibrium position where this electric field lines are matched or kind of held in equilibrium. The force on this, the magnetic force, the net magnetic force operating on this mass M, because of the interaction of this fixed magnet and the electromagnetic field lines generated in the coil, this will be going back to an equilibrium position depending on the acceleration that this mass M sees, right? Let's try to make a model of this, and then probably we can understand this a little bit better. So what we have is an acceleration. So this is a vector quantity, which is our input to the system, and this acceleration works on this mass M, right? And this inertial force is being, so we have an inertial force operating. So let's say the body is moving in this direction, so the inertial force operates in the opposite direction, right? However, we also have a magnet here, which will ensure that, you know, if this guy is moving away, the equilibrium position will be such that this magnet will operate such that it is going to try to pull it back here, right? And how does that happen? It happens because of the negative feedback mechanism. So we have, so this is that, so this equation you should be now very well aware of. This is this is the same force on the, I mean the spring and the damper system, which is a second order equivalent, right? So this mechanism, this whole thing here gives rise to this module here, right? Multiplied by KD. KD is nothing but this guy, but from the potentiometer displacement, right? This probe keeps moving, and based on that, the voltage that is seen by the transconductance amplifier changes, and this you can think of, you know, this resistance here, the gain that you see because of the movement, you can equate it to, you can say that, okay, there is a gain KD here, and then we have KA. Actually, this KA, it's more appropriate to say that this KA is nothing but the transconductance of the TIA. The output current goes and creates a magnetic field which works in opposition to this magnetic coil, and the relation between the output current and the magnetic field, which we are well aware of from our, you know, class 12 physics. But here, for sake of simplicity, we are representing this as a constant Kf, and this, the interaction between this electromagnet and this magnet and the coil is represented by this summer here. And what do we measure? We are measuring the current that is actually flowing out, but then instead of measuring the current, we have just a resistor placed here. So this current gets multiplied by this resistor value, and this is the output voltage that we measure, right? So any question how this block diagram is formed? Okay. So if there are no questions on the block diagram is formed, then if we do the math, which I'm not doing again because there's no point in writing a simple set of equations to form the transfer function. This I leave to you guys if you are interested in actually forming the equation. The V out by acceleration, you will see you will end up with such a term, right? You can do the math, nothing interesting as such, other than just forming the equations and kind of taking it to a good shape, right? So this is one. Now what we see is we have now more controllable parameters here, given by Ka, Kd, Kf, right? So if we now make Ka large, Ka means this transconductance, if we now make it large, so that so this term becomes very large, right? What I can do is I'm just rewriting. So let's say this large or small, that we'll see later. But the fact is we can make this term very large, and then I'm rewriting, instead of omega n, I'm rewriting the expression as omega ns. So this is an ks. I'm just rewriting this expression where this term comes. I'm just rearranging, and what do we see? What we see is the omega ns in the feedback system, the sensor system, the natural frequency of the sensor system now is omega n multiplied by a factor here. So omega n is the same omega n that we saw in the seismograph system, assuming that the mass and the constant and the spring constant k in the seismograph we had denoted the damper coefficient as b. Here it is lambda, but that's fine. But the thing to take away is, because of this feedback mechanism now, what we see is the natural frequency of the feedback system now is omega n multiplied by this factor, which means, and of course the eta also. So this is the modified in the new feedback system. The damping coefficient is also now modified. And one thing you can see is the damping coefficient is much smaller now, right? And you can see, in a way, what is the disadvantage that you see in this equation, right? Do you see the problem as such? And see, these are the questions you will probably expect in end semester or this thing, right? I'm not going to give you any straightforward question wherein you can just Google or copy or that you'll never get, right? But the point is you will have to get an understanding or a physical meaning of the system. So if you, by looking at these equations, right, as a designer, right, what comment can you make? Anyone? So I'm trying to drive home the fact that, look, by giving a feedback, we are able to increase the natural frequency of the system significantly, right? So that is one positive comment, right? But we have done so much of stuff. We have put in electronics, some sort of electromagnetics, and after doing all that, we see we end up with these two terms. So any comment that you can make? Anyone? So the comment that I can make is that, look, yes, I have been able to improve the natural frequency of the system significantly, right? Which means essentially the bandwidth of the system is now much higher. However, even after doing all this, I have not been able to, I do not have separate controls for omega ns and eta. I repeat what I mean. So if you look at the seismograph, right? The seismograph equation we had, right? What did we see? We had omega n and eta. So this was omega n square and this is eta, right? So the only variable that I have in my control is k for omega n square, and once k is fixed, the other variable that I have is b, beta, right? I mean this b, with which I can control eta, and both of these are mechanical constraints. I do not have, as electronics engineers, I still I mean, these are mechanical constraints, and that is fine because in this there is no electronics here, right? But in this, I have already incorporated electronics, right? And in spite of that, if I see, I have not been able to decouple the damping coefficient and the natural frequency any more than what it was already. Is that a fair statement to make? Because if I increase this guy, eta is reducing, which is fine. But then I do not have completely separate controls, right? I still have to rely on the choice of the damping coefficient lambda and the mass m, which are physical parameters. I do not have any electronic control with which I can decouple omega n and eta s, right? Any comments? Is it understandable what I'm trying to say? And see guys, this is what you will expect from me when I set questions, right? You will expect that probably I will give a twist somewhere and then expect you to identify the advantages of the proposed system over the existing system, right? Or maybe I will ask you that maybe can we do a simple a simple modification to the system wherein I can get separate controls for eta and omega n, right? Anyway, so we'll see what to expect in the exams later. But so the point is, this is the kind of approach that I would like the students to have. That you should have some insight into the subject rather than mugging up some equations. Equations are not. I don't expect you to remember equations. I have been telling this from the very beginning, right? All what I expect is understanding. So omega n is much higher, and the eta is much lesser compared to, and can be controlled to get critical damping. Yes, we can adjust these parameters to get critical damping. But these two, I mean, in an even better system would have been where omega n and eta can be separately controlled, right? Wherein the damping coefficient and the natural frequency are not kind of tightly coupled with each other. Here, the only separate controls that we have is m and lambda to decouple omega n and eta. Yes or not? Any questions on this? Okay, so now we are going to look at a little bit more. And again, these are all what we are discussing is the concept of feedback and its application on real systems, right? So first, in the very first class on this topic, after the mid-semester, we looked at how feedback helped in a simple electronic system, and the system was completely electronic. Second, we looked at inertial sensors. And now we are going to look at pneumatic systems and see how the concept of feedback can be applied to our advantage, right? So, and in that context, we are going to look at pneumatic systems. And what do we mean by pneumatic systems? These are used in industrial applications, and typically these pneumatic systems are made of either air or oil. And why do we call it pneumatic? A simple Google will tell you pneumatic means it has got something to do with pressure, right? Right? And these pneumatic systems we will actually use to measure, so we'll see what we'll use to. But for now, let us just look at the difference between a pneumatic and a hydraulic system. So we actually will look at. One second, I'll just see. I'm just coming to the hydraulic part. I think I'm just trying to see whether we are going to discuss the hydraulic part or not. I think we will be discussing. We will be discussing hydraulic systems towards the end. So anyway, one second, I'll just go back to I'll just go back to the I'll just go back to the sorry for I'll just go back to the so we'll discuss both the pneumatic system as well as hydraulic system. So what are the disadvantages? And so let's do a quick comparison of both these two systems, and of course we'll look at feedback. So the pneumatic system, it is compressible. Hydraulic, it is not compressible because it is kind of understandable. Pneumatic systems, because it is made of air, I mean, we take help of gases which are easy to compress, right? But hydraulic system will be made of fluids or oil, and it is relatively difficult to compress, except until and unless we apply a very high pressure. Lacks lubricating property, and this is also understandable because air will not work as a lubricant, right? So all the moving parts of the sensors will undergo a little bit more wear and tear. However, for hydraulic systems, because the fundamental mechanism involves a fluid, a liquid, we can use the same liquid as lubrication of the overall system. So this will, the hydraulic system probably will be a little bit more robust. Lower operating pressure, and this is higher operating pressure. This is again understandable because this operates, the fundamental element that we are using is gas. So, we probably cannot apply too much of pressure, but because this is operating with oil, we can apply a little bit more. I mean, not a little bit more, we can operate these at significantly higher pressure. Lower output power, and this is higher output power. This again is understandable because, whenever you have material which can tolerate, higher pressure, or it is more robust, you will expect that it will be able to deliver more power, right? Low accuracy of pneumatic sensors, especially at low velocities. Higher accuracy of hydraulic sensors hydraulic actuators for all velocities. And then external leakage is permissible because it is gas. A little bit of leakage is okay. We don't probably care. However, internal leakage has still got to be strictly avoided. Here, internal leakage is permissible, but external leakage needs to be avoided because you don't want the oil or the liquid that you have in your sensor or actuator, right? That should not be flowing out of the system, right? Here, internal leakage has to be strictly avoided because if there is internal leakage, right, then the basic bounding equations will change. However, external leakage will kind of qualify this statement when we discuss the actual systems. No return pipes are required. Return pipes are required. Operating temperature 5 degrees C to 60 C. And operating temperature, of course, is little bit wider, not little bit, significantly wider. Fire and explosion proof generally, because this is gas, generally, not much in terms of, fire and explosion, but the fluid, because we are using oil, it may be highly inflammable, right? So let's discuss the first pneumatic system. And here, what you see here is we have a pipe, right? So by now we should be well comfortable with the concept of operating point, right? Both electronically, and you can think of the operating point in similar terms in mechanical domain, right? So we have the operating fluid or the operating air around this has a pressure P, and there is an incremental, a small pressure change that will happen in the environment, which let's say we need to measure, right? And here we have a nozzle kind of a thing, which in electrical terms, this is equivalent to a resistance because, and this is again understandable, you are trying to, let's say, pump in the gas, but then because of the nozzle, because of the dimensional difference, this is going to resist that change, right? If you are pumping, so if there is, if this diameter of this nozzle is larger, what will be the value of the resistance? Just think simplistically, right? No equations, nothing. What will be the value of the resistance R if I make the diameter of the nozzle larger?
Less.
So it will be lower.
Exactly, it will be less, right? So we do understand now. One second, let me have some water, please. Yeah, so we do understand that this nozzle will work like a resistor, and because of that resistance here, we do not expect the change in the input pressure to be reflected as a change in the output pressure in the vessel. So the output pressure will be related to input pressure, but it's not a one-to-one relation, right? There will be this resistor here is going to play its part, right? So let's see how it is going to play its part. And so this is the delta P versus Q. Q is the quantity of the air that is changing here, right? So as you see, the higher and higher we apply, the delta P becomes larger and larger, the amount Q is going to increase, but then it is not a linear slope, right? So there is a non-linearity, and around that operating point, we can say, if as long as delta P is very small, it is fair to assume that the resistance will remain constant. But it is still important, I still drive home the fact that please note that inherently this system is nonlinear. This resistance offered because of the airflow inherently has a nonlinearity. However, for delta, like incremental small quantities, we can assume this to be linear. And so delta P is nothing but the input pressure minus the output pressure, and R is the slope on this curve. And what is C? So this we are saying this is a capacitor, and this also is kind of understandable, right? So if you can think of the air as current, right? The air is actually, the gas is actually being stored in a container, right? So this is equivalent to the charge getting stored in a capacitor, right? So if we can think of this container as a capacitor, we can define the capacitance C as change in the gas stored divided by change in the gas pressure, right? So what is change in the gas stored? So this is delta Q, right? Delta Q meaning in electrical terms, and change in gas pressure. So this you can think of as delta V, right? The voltage. So the change in the voltage that you have across a capacitor is going to result in the change in the charge in the capacitor. Synonymously, we are saying that the change in the gas pressure is going to result in the change in the amount of the gas stored, right? And so this relation is going to give us the equivalent capacitance of the system here. Any questions? Okay, so what is C? C is the delta in the gas, change in the gas stored, delta M divided by delta P, right? Which means, and this comes from simple, the total mass that has changed is the volume. Our volume remains constant. So what would have changed because of the pressure is the density, right? So a simple mass into volume, mass is equal to volume into density. The volume remains constant, whereas the density changes. So this I can write, right? No big deal here, right? Mass is the M equal to mass of the gas vessel, P is the gas pressure, V is the volume in the vessel, and rho is the density, right? So capacitance of the pressure system depends on the type of expansion process. This is very important. See, what we need to understand is the fine print, right? The equations are valid, but the equations are valid under certain conditions. We cannot assume that this whole thing is going to behave like this under all conditions, right? So we are saying that it depends on the type of the expansion process, and wherein we can use the ideal gas laws, right? So the ideal gas laws again you have to rely on a little bit of physics for understanding sensors, right? But this is, I think, pretty simple enough to understand. This gas law you are kind of well aware of. So this is an exponent, n is an exponent, but this is our, for ideal gas laws, we can say this is the expression that we have relating what? Relating the volume, the mass, and the pressure. So the pressure, volume, and mass with an exponent n is constant, right? So for ideal gases, we can write PV is equal to P divided by rho. V we know, right? P we know. So one second. So if you see here, let's focus on this PV equal to RT. This we know, right? Pressure, volume, the R gas, and T is the temperature, right? So V is the specific volume of the gas, and this V bar is nothing but volume occupied by 1 mole of a gas. This is a gas constant, and M is the molecular weight of gas per molecule, molecular weight of the gas in per mole, right? Molecular weight of the gas per mole, right? So these, these gas expressions, I think, so these equations you would have dealt with. I'm just revisiting those. I'm not going to discuss this, but now the point is, why are we doing all this? We have to come up with an expression for the capacitor C, right? So del P, del rho. So V we know, and del rho, del P. This is what we are interested in, right? The change in the density divided by the change in the pressure. So del rho by del P is given by N is an exponent, is a constant, polytropic constant. Gas, this R gas is again constant depending on the kind of gas you have, and the temperature T, right? So what do we see in this? The capacitance that can be equated, or that can be thought of in this kind of a system, is dependent on the volume V of the vessel, the kind of gas that you have, R gas, and the temperature, right? So capacitance is given by, this is understandable? And since capacitance is, since this is this, now I can write C is equal to del P, C del P del T. So where is today? Okay. So C multiplied by, so C into dP0 is equal to Q into dt. Can we write this? Can we write this portion? We already have, right? The capacitance is related to the change in the gas core divided by change in the gas pressure. Now what we are doing is the capacitance multiplied by the change in the gas pressure, right? Del P0. Capacitance change in the gas pressure is del P0 is multiplied by Q, the amount of gas that is flowing in through the orifice, multiplied by time. Please note the capacitance C. So this is, can you relate this to our equation, to our capacitor equation, Q equal to CV, right? So basically, if you see, right, so Q I can write as I into delta T, right, is equal to, I can write something like this, right, I into delta T is equal to C into delta V, right? So this is what I am writing for the gas, the pneumatic system here. Is this understandable? Do you want me to explain this further? C is the capacitor, P0 is the change in the gas pressure here. The capacitor multiplied by the delta V, which is the delta V with the voltage can be equated with the pressure associated with the system, right, is equal to the total mass that has flown into the system, right? And the flow rate was given by Q, and the flow rate is given by Q, and dt is the time that is associated with the change in pressure. I mean, there is we are talking of the change in a certain given time, right? So the delta, the PI has happened in a certain given time, and the output will respond. The PO, the change in the output pressure, will take some time to respond, right? And that, let's say, is given by dt. So we'll stop here, and probably from tomorrow we'll pick up from here, right? Let me stop today. Tomorrow we'll start from here. Okay. So thank you guys, and have a nice day.